about lattices. So let's let L sub n, this is the space of, this is a moduli space of lattices, you know, lambda inside R to the n, and what equivalence relation modulo rotation. And oh, I forgot the word of oriented. Up to rotation and scaling. Okay, so we talked about L sub 2 last time. We showed that L sub 2 can be identified with upper half plane modulo the action of SL2Z by linear fractional transformations. And so we want to think about what is that, what can we say for higher n? And so I want to make the so let's say that we consider some equivalence class of some lambda inside there. We can lambda is equal to m times z to the n for some matrix. So m, and after we are allowed to scale our lattice. So m is in general going to have just a positive determinant. It'll be an invertible matrix, and lattice, you know, determinant negative. But after rescaling, we can assume that m is inside SLN R. Okay? Because scaling the lattice just scales the determinant in this matrix. Okay, so in other words, another way of saying this is that we're saying that, you know, you take an n by n matrix of determinant 1, you take the lattice that's spanned by the columns of that matrix. Okay, so every lattice can be written in this form. And so now, so, you know, this m, so m times z, another way of thinking about that, m times z to the n, that right there is the image of the map that goes from z to the n, matrix multiplication by m in to the right there. When I say it like this, you see that there are natural left and right actions. So of SLN on the domain, right? We have an action of SLN R on the range. And so we have an action, we have actions, have commuting actions. Commuting. So actions of, well, it's going to be SL in Z, a right action, if you think about how you compose from right to left for functions. Also of an action, well, I could say it's an action of SLNR, but in particular of an action of SON in SLNR on the codomain. That left action. Okay, and so we see then is that you know, modding out this rotation business, right? Modding out by the action of SL and Z corresponds. That takes care of the fact that, you know, when we do this, we're implicitly choosing a basis for Z to the n, right? If we change the basis for Z to the n, that doesn't actually change what lattice we're thinking about. It just changes how we're writing it. What we see then is that the space of lattices, we've written as a double coset space. It's the cosets. We have SL in R. We mod out by S. On one side, we mod out by S L and Z on the other side. It's the space. That's right. Okay, so this is metric object that we want to understand in some way. And so let me. So to do this, I want to sort of two pieces, and so let's define x sub n to be equal to this just one of these quotients, SLNR modulo SON. So SON is a maximal compact subgroup of SLNR. It's obvious, and there's no larger compact group. Any compact subgroup of SLNR is SON. That's a basic fact about Lie groups. Example of what's called symmetric space. And every space can be written in this form where you choose some semi-simple Lie group and you mod out by a maximum group. So we have an action of S ln Z. L sub n is the quotient of X sub n by S ln Z. So what kind of space, what kind of topological space is X sub n? I want to remind you, back, last time you taught linear algebra, you probably taught the QR decomposition, right? So the Gram-Schmidt process, what that implies is that every element M inside S, L, and R can be uniquely as what as the something, so it's going to be which one must be Q and which one is going to be R. Obviously, I haven't taught linear algebra. I'll call it C times U. So C is inside SO as M is equal to that. C is inside SON, and U is triangular. Trying to take this matrix right here, we're trying to turn it into a matrix whose columns are orthonormal, right? So what do you have to do that? Well, the first thing you do is you set the first column, right, to make it have length 1. Then you add a copy of that first column to all the remaining columns to make it orthogonal to those columns, right? That's like one row of this unit, right? I always forget. I keep track of actions. The next, you do the same thing to the second column, but then you don't need to add anything. The second column only needs to be added to the fifth and so on. And so then you see that process. That familiar Gram-Schmidt process really is writing. You take C, that's the result of the Gram-Schmidt process, and sort of undo it, and that's U right there, this upper triangular matrix. Now, the space of upper triangular matrices, so upper triangular matrices, the entries are there for 2. So we see that as a topological space. So as a topological space, so sub n, then we see it's the same space as the space of upper triangular matrices, and that's just to the dimension of the space upper matrices. So this is just Euclidean space. This is no like, it's not a group, right? So, but that's what this space is. This really is Euclidean space, written in a funny way. So, thus, what we see is so X is contracted. So SLNZ, it acts on X sub n properly, and the stabilizers are all finite groups. And why are the stabilizers all finite groups? Well, SL stabilizers are subgroups simultaneously, both of SL and Z, right, and also of some discrete compact groups, and those are finite groups. Okay, so it's properly with finite stabilizers. Yes.
Don't you have to consider non-singular one less dimension?
Yeah. Keep track of these things. So, right, yeah, I don't want that. Well, and this term has to be 1, so that cuts down the dimension. Okay. So it acts in that property with finite stabilizers, and so thus we see from last time the moduli space. So space n, which remember that right there is X sub n below S with Q coefficients is the same as the cohomology SLN coefficients. Okay, so space has the same rational cohomology as SLNZ. It's almost a classifying space. It's sort of a rational classifying space. If this were really, this would honestly just be an honest cage tractable space by a group acting properly and freely. Space, you know, and in this, but we only put the word Q there, so it's like a space. This is like I did last time, and so therefore, you know, we're interested in the topology of L sub n because we're, you know, one reason to care about it besides the sort of fact that it's a natural space that somehow it's one of those things that nature provides and we, you know, so we do have to understand it, but also, you know, SLNZ is a very natural group. We'd like to understand its group cohomology. So let me give you an alternate description, just an alternate way of thinking about X sub n, which is add some light onto that. So here's an alternate description of X sub n. So is that X sub n is also the space of inner products. So this is the space of positive definite. So symmetric. So in matrix M, and I just say determinants equal to something right there. Symmetric M by M. I shouldn't call them M because I've been using M for other things. I'm going to call these things A. Okay? Why is that? So the for this is I want to make the observation. So this you know, we have that X sub n is equal to, so what I need to show is that it's equal to the quotient of SLN R modulo SON. Well, first, SLN it acts Xn via the sort of usual thing. So if we take some matrix, an element of A, that's supposed to simply be, and I guess this is supposed to be a right action, not a left. So A times M, it's supposed to be, what is it? It's M transpose AM, for here we have that A this action from linear algebra, right? It's like the equivalence of inner products. But I mean, this is transitive. So since positive definite forms are equivalent, or are equivalent, in fact, from there's only one positive definite in the end. And the stabilizer of the identity, stabilizer of A is equal to the identity matrix ON, right? And so see, we can identify this. We have a transitive group action. So this is a homogeneous space with respect to the SLNR, right? It's a transitive action, and the stabilizer of a point is SON, so it is the space of cosets. And so this is another very sort of natural think about space of cosets. Okay. You can write down things, and this is the form in which most people that are doing computations in the symmetric space, this is the form in which they think about it. There's like various triangulations of it and things like that people work with. Okay, so what I want to talk about now is I want to talk about the cohomology of SLNZ via space right there. But I'm going to start off with something that's a little bit more general. So I'm going to move left here so I don't have to keep like back and forth. So more generally, let's think about the cohomology not of SL and Z, but of any inside SL and R. So more generally, let's consider a lattice. So gamma inside SL and R, e.g. gamma is equal to SL in Z. Okay, SL and Z is the one we really care about. I talk about true for any. Now the word lattice is being used on the board in two different ways, right? They both mean a discrete function has finite volume, but they're sort of lattice in a non-abelian Lie group, right? And lattice inside, I guess if I write it down, inside R to the n is a lattice in an abelian Lie group. R to the n is an abelian Lie group. But SL and Z is lattice. It's like the canonical lattice inside SL and R. Other lattices inside SL and R. For n at least 3, Margulis one is few instructions, but lots of them, and they are very different problems. And so how could we compute the cohomology? Well, the cohomology, still of gamma with, and I'm going to switch to real coefficients because that's makes what I'm about to do. That right there is, again, it's the cohomology of the quotient of this space x sub n by our lattice with real coefficients. And how might you compute this cohomology right here? Sort of natural thing. So this is not quite a manifold. It's pretty close to a manifold, but because gamma might fix some, there might be some finite stabilizers. It's sort of manifold, right? Their singularities correspond to the fixed points of gamma. But it's close enough to a manifold that we can try to compute its cohomology using de Rham cohomology. And so this right here, this is de Rham. So this right here is the same as, and I'm going to change that, there's 3 indices, and so I'll change that to HK to make the indices work. HK of the de Rham complex, the complex of different forms on Xn below gamma, right? That's what the de Rham theorem says. And now, as I said, what does that even mean? This is quite a manifold. But an easier way to think about this is the same. The complex, we're going to take differential forms on X sub n, which is like literally a Euclidean space right there. What is that? What does this superscript? That superscript means, this means invariant forms. Let me erase this so I could write something right here. So the superscript means gamma invariant forms, right? It's just sort of standard notation for taking invariant script. So a differential, you could fit to the universal cover, right? We get a differential form which is invariant under the deck group, under gamma. And not quite acting freely, so it's not really a deck group. It's like a deck group for a branch cover. Okay? So we can compute this using gamma invariant differential forms on the universal cover. This doesn't seem to bias much, right? But there's something remarkable. There's one way that we could try to make some computations here. So we want to figure out how could I... And so here is an observation. So we call this G being S LNR, that's our Lie group. So we have an inclusion. We could look at differential forms on X sub n that are invariant not under gamma, but under the entire Lie group. And so that lies inside differential forms that are invariant under the lattice, right? Because we're looking for conditions. We want to be invariant under the entire Lie group on this homogeneous space for G. And so now I can state an amazing theorem of Borel. This is called the Borel. That the above induces an isomorphism between the kth cohomology of the space of differential forms under G and the cohomology of this, which remember that computes the cohomology of gamma. So that's HK gamma with real coefficients. That's not true. In large relative to K. Okay, so if we're looking at n is at, and you can compute like of this complex of G invariant differential forms. Now there's now that's actually quite good. You might say this doesn't look. Taken one calculation I don't know how to do and replaced it with a other calculation I don't know how to do. But you can actually compute this. Is that the left-hand side can be computed. G natural form, this is determined by its value at a single point. So this is like a, determined by like Lie algebra data, right? By infinitesimal data. Can be using Lie algebra cohomology. And in fact, we have that for, in large relative to K, we have that the left-hand side is isomorphic to, it's going to be a polynomial ring. Classes C1, C2, and so on. And we're going to take it in degree K. So the degree of C sub I is equal to what? It's going to be 4I plus 1. So the first class 5, and then class 5, 9, I can't add today. Class in degree 5, a class in degree 9, a class in degree 13, and so on. And these in differential form too. Okay, we can really calculate. So this is a real calculation. The proof is, you might ask, how could you prove such a thing like this? And I don't want to say much about it, except yeah, you're right.
And this is true for all of SL and R?
This is true once in, I said K once in is large relative to K. Claiming calculation range. Yeah. Yeah, this is true for SL and R. I want n bigger than K. N to be huge, cohomology, I'm looking at it to be small. Right, but like that, those degrees go to like there's a range of n. You might say that sounds like shit. That's like a lousy calculation, right? But it really, there's no calculations of this form. So this is almost calculations we know. Once n is sufficiently large. I'll tell you the other ones actually. There's a finite list of other notations. Once n is sufficient. So yeah. So is that structure? So what's going on here? I'll say this in words. So X sub n has a natural Riemannian metric. Because symmetric, it's like SL and R modulo SON. You put an SON invariant Riemannian metric at one point and you move it around by the whole thing. And that metric has non-positive curvature. It's a very nice Riemannian metric. And it turns out that these forms are actually they're harmonic forms with respect to that metric. And so what this is sort of saying is that at least in some range, you can compute the Hodge theory. And so that's what happens. It's bigger, you can control the growth of forms near the boundary enough to make the Hodge theorem work. But that's how the proof works. Anyway, that's all I want to say about that. Hopefully that answers your question. So, I know it's an audience of geometric topologists, and I just used the word Hodge. I'm not going to say the word Hodge theory again. Don't worry. So, okay. So this is a nice calculation. So let me make two observations. So here's two observations. So the first observation is that for gamma is equal to SLNZ, so this is the first observation, so 1. For gamma is equal to SLNZ, the left-hand side is independent of n, for n large, right? So this thing here, this computation, you see like there's no reference to n in this, right? So this says that I, so the hk of SLNZ with respect to r is independent of n for n large. You could even say, I think the work of Potts and Miller, and I'm probably forgetting a couple, Coopers and Senator Coopers. You can take this to be like than k. Okay, that's so this is true. In fact, this is true. This is true for over z. Let me give you. So this is what's called homological stability. If you haven't seen this before, so well, let's think about the first. Let's switch from homology. So 1. With integer coefficients, that is SL2Z abelian. That right there, Z mod. That's because SL decomposes as a free approximation of SL4 amalgam and the abelian is H low of SL in Z is equal to 0 for n at least 3. SLNZ is generated by elementary matrices. EIJ, that's just the matrix. You take the and put a 1 in position I. You can write elementary matrices as commutators. So, and if and if I, J, and K are distinct, then we have this of E, I, K, and E, K, J. So for n at least 3, J die in the abelianization. Right? So we see that, H1 starts off with this funny Z mod 12 for SL2. But starting for SL3, H1 is 0. Something happens for H2. Chunk for small n, and then it just stabilizes. It turns out to stabilizes to Z mod 2. That's a theorem from algebraic K theory. I don't remember what H3 is. So what H3 is stabilized. H stably irrationally at 0. Okay. So that's the first observation right there, is we have this homological stability stuff. The next observation 2, this is even more shocking, is that this, I want you to notice that the left-hand side is also independent of this, right? This right here, no reference to gamma inside it. So of gamma, take the G variant forms on this, independent of the gamma. Okay, so as this G. And really surprising fact, there's a lot of lattices inside SLNZ. They have very different group kinetic properties. Some of them, for instance, co-compact lattices. For SLNR modulo, the lattice is compact, and so therefore the math like that's, you know, it satisfies Poincare duality, and there are lattices that are not co-compact, so the cohomology doesn't satisfy Poincare duality. Like, therefore, you know, like the cohomology, at the stable range, it doesn't matter what lattice you choose is. Okay, that's, I think, a really shocking fact. No reason for that to be true, except the theorem is true. I mean, there's a good reason that tell you a cartoon story. So it's just that it's a special. So we've already seen these congruent subgroups. So let's let gamma n of L be the kernel of the map from SLNZ to SLN Z mod L. So these are called the congruent subgroups. So these in SLNR, because you know, find it doesn't make you multiply covolume by whatever the index of the subgroup. And so what does it say? The above says that for n large relative to k, so SL in Z with, you know, R coefficients is isomorphic to A of gamma in L. Subgroups doesn't change the homology. That's a very unusual phenomenon. You expect a finite index subgroup, it's like passing to a cover of a space. When you pass to a cover of a space, you expect the homology to get a lot bigger, right? But in this case, it doesn't. Say that this is over even for A1. The abelionization of these congruent is much bigger than 0. Okay, so what it is, I don't have time to actually do the proof, even the proof is not hard. I can tell you in the proof it's not hard. It is isomorphic to n Z mod L for n at least 3. And so this is a group of L over Z mod L, right? It's a finite abelian group. Oh, yeah, that's not a true statement, but it's a true statement. Yeah. Now, yeah, the abelionization. That's probably in. I can explain. There's a beauty for this. Do this through my note, which I'm. So, anyway, so that's what I want to say here. So this is the stable information about cohomology. How about How about, because people were complaining, like, why do I care when n is large? Are roughly the same. What's the cohomology there? And more interesting question. So, not more questions. So, questions. So, the first to places that's useful for me. The first one is so we know that the shows that the homology HK of SL in Z with at least Q coefficients is finite dimensional for in, sure, is this true in general? Is it true over Z? Right? Because, you know, who knows? I'd say, aha, this is, you know, it's the homology of this manifold, this X sub n modulo SL and Z, but that's like non-compact manifold. Non-compact manifolds, of course, who knows what, you know, what kind of finite homology has, right? One question, you know, are there finite properties? Another question, so the, you know, the dimension of, you know, X sub n modulo SL and Z is equal to n plus 1 to minus 1. So we know that HK of SL and Z, at least with Q coefficients, is 0. Or I'll say this, so since we've already been having people talking about cohomological, we know cohomological dimension over Q of SL and Z is less than or equal to n plus 1 choose 2, 1. In fact, you can say this too because this is a non-compact manifold, so we know that actually it doesn't have any homology in its top degree. So what is Q of SLN Z? Okay, those are sort of two actions going up. They were answered by in a theory. It's a theory for relativity. It says that so they so they showed that this space right here, so X sub n is the interior so X sub n R has corners if you want to have the smooth structure correct, right? So it's a manifold with corners. So such that I mean, not bar modulo SLNZ is compact. And so we see that of SLNZ is always functional. Over all, then it's you can do like little spectral sequence arguments to get as well. So they constructed a fortification of this space, right? They, as the interior of a manifold boundary, and so the quotient is a compact manifold. Okay, so that gives us finiteness. Because a compact manifold has finitely degenerate homology. But they also they didn't just this in some sort of abstract way. They also understood. They also understood the boundary of F to prove that cohomological dimension is actually equal to 2. So it's much smaller than n plus 2 minus 1, right? Okay, I might, depending on how the timing goes, it's like at the end of this talk. So let me now tell you. So the next place where you the sort of opposite, the least stable homology, the homology that's least described by Borel's stability theorem, thus occurs in near degree in choose 2, right? And so, question. So what happens HK in Z for K near in choose 2. There's not that many computations that are known. Full rational cohomology ring of SL and Z is Moduli, by number theorists and algebraic K-theorists. You would triangulate X using what are called void tessellations. But the problem is tessellations grows fast that eventually computers cannot actually calculate. So there are tables up to n equals 7, and at some point, I sort of made it was like arrange a nice enough way to note a pattern. And so here's a conjecture that was made by me and Tom Church and Ben, which is. So here's a conjecture. This is Church, Farb, and myself. What does it say? It says that use was it? So it's Q Z with Q coefficients. This is called. So sort of should be some version of Poincare duality. This is like the Poincare dual classes. For n large enough, for n. So I know this is exactly true. N equals 7. And so what's the more evidence for it than that? So here there are known cases. There are 3 cases that are known. The first 0, which is due to I'll say it like this. So Lee and Charba. This was back in the 70s. They proved K is and that was the other conjecture. It was true for K is equal to 0, true for 7. Proved it equal to 1, so it's true in codimension 1. And even more recently, there's a long list of so Brook, Miller, Peter, and Jenny Wilson. I was missing Fruka. Okay. So it's up to codimension. And this to get toward the all bets are off. There's the number hospital co-modeling. So but I think this is a very intriguing conjecture. I should say that, one consequence, if this conjecture were true for K is equal to 3, I believe, what K is equal to, we need K is equal to 4? Yeah, if this were true up to K is equal to 4, then we could resolve one of the last, so the next open case of the algebraic K theory of Z. So the algebraic K theory of Z, except for some weirdo Z mod 2 factors in degrees that are by 4. So, and that would give K12, I believe. So K is 0, and if you believe some very subtle. So, anyway, another thing you could ask about. So, if you're paying attention, you should be a little disturbed by this conjecture, right? Because this is a dimension, but the topology is 0 in the cohomological dimension. So, what gives, right? The point, remember, we see in lecture cohomological dimension, it should be the top local coefficient system, not just the constant coefficient system, right? And so you might ask yourself, what kinds of coefficient systems? Another thing that's sort of equivalent is, can you pass to subgroups that have cohomology in those degrees? And in fact, there is a, this comes back to these subgroups. Okay, so what's group cohomology? Cohomology is like X of over the group ring, right? And so you could plug in. So usually if you define trivial coefficient x of z comma z, right? You could replace one of those z's with a representation of the group ring. That's a local coefficient. Or just a notion of a system on a space. Representation of the fundamental group gives you a constant cohomology with respect to that. That's why I don't want to say more than that. You can see like a bunch of definitions, none of which are super short. So, let me think though that so the reason allow coefficients since cohomological dimension cannot so what they did, where they proved this, was they actually that if in the cohomological dimension and coefficients 0, so and they conjectured a very natural for it. Okay, so this was made in the 70s. It was for n equals 3 by Avner Ash, but using things that are very special for n equals 3. Okay, so, but it was disproved in the 80s, and then people forgot about the conjecture. It was for false for all things. But in fact, they proved it equal to, they didn't explicitly do 2, but their methods can do 2, and they explicitly prime 3. Okay, another theorem of myself, contrasting behavior to the opposite of the stable. Stable, you pass it to z to one of these congruent subgroups, it doesn't change cohomology, right? But in this very unstable range, it causes it, in fact, not just to get non-zero, but to become huge. Stable loading pass to these finite index subgroups. In this theorem, this is due to Pot and myself show that this conjecture is true for p less than or equal to 5, and it's false otherwise. And in fact, we gave even more unstable cohomology. We gave an enormous amount of sort of unstable. We don't really know how to. I can't imagine that what we constructed is everything. Definitely, like so. There's no reasonable conjecture for. So, I think the patterns just what's special about the primes 2, 3, and 5. These correspond to, you can look at the cover of the curve, upper half plane mod SL2Z. That's a surface, like a topological surface, and it's got genus 0 for primes 2, 3, and 5, and it's got positive for larger primes. That's sort of responsible for the failure of this conjecture, is the positive genus, the sort of weird interior cohomology. So, what does that mean? I don't even know what that means. So that is, let's see. That's remaining. Okay, good. So what I want to do now is I want to say just about, first, are there any questions or picture of the unstable cohomology? Sort of, this is, I've told you all the results that are true, like n is bigger than 10 or so. Let's see here. So, okay, so how does the proofs of these, how do they go? What they go through, they correspond to very carefully studying the boundary of this compactification. So I need to tell you something about the boundary of this compactification. And so I'll do this right here. So, Burrell and Sayre, they gave a formula for homotopy type boundary. What's called tell you so definition. So the Tietz building. So which there's only so many letters in the world, so I'll call it Tn of. I'll just put a field here. That's a field. So in a multiplicative complex with simplices, I guess I'll say, R simplices. So 0 is properly contained inside V0, properly contained all the way up through V sub R, which is itself properly contained inside F to the n. So you just look at flags of substate of F to the n, okay? And those so for n equals 2, T2 of F, this right here is the discrete set lines in F, right? There's no line in a plane that are properly contained inside F2, right? So this is literally F2. Just projective space. It's a space. It's the projective set, right? So, what was that?
Last V R minus 1 then, in order for the...
No, it's a 0 dimension of, so complete flags, right? This so you can pass the boundary of a flag by deleting a smaller flag.
But it looks like in your description, there's sort of an interesting thing.
That's V0, right?
What?
So the only interesting, so V0, so you can't have V0s contained inside V1, right? Because they're all proper containments. So so thus I'll say like so. So R is less than or equal to n minus 2, right? You can have at most n minus 1 things in a flag, but start indexing at 0. Does that make sense?
Yeah. Oh,
yeah. There's
R in the end.
Yeah. Indexing convention never keep it right. So, and in case, for example, just to keep, so T3 is so the vertices and plane are containment. Connected by part-type graph. I'll tell you the proof of the, it's enough to show that you can get a path. Because every plane contains a line. These two lines, that's a plane that contains them both, right? Okay, this is just a connected graph, but it's a very tight, it's very tightly diameter 2. Okay, and for higher n, it's got, those higher and higher simplices. But here's a theorem. This is due to Solomon and Tietz. What it says is a discrete, it's also called a zero sphere, right? A connected graph, almost up wedge, right? You just maximal tree. Continues, it says that T n of F is homotopy equivalent to a wedge of a bunch of the spheres of the dimension you expect. This is the dimension of the space, right? very beautiful, this is a beautiful little piece of topology. Now proof that's very hard. This is, again, I can do this to you during the break, right? It's like there's a 10-minute, as a fun 10-minute, which I have to think about. It's a fun, so I've given it in lecture before. So this is definition. So I should say that the Steinberg module or the Steinberg representation of GL field is, well, we'll call this ST n of F. This is the non-zero homology, possible non-zero homology group of this, Tn of F with respect to whatever coefficients you want to put on here. I don't know. Let's just say, I don't know, Q coefficients just to want to. This is a, so this is a vector space. With a GL in F. Because of course the general linear group acts by permuting lines and planes and so on, right? Very interesting GLNF action. It was introduced by Steinberg in the 60s. And he was interested in the F as a finite field. And one of his theorems was that when F is a finite field, this is a useful representation of GLN of that field, which an representation of it. Like, it acts on the field to the end, but that's not a characteristic zero, right? So this is actually one of the sort of building blocks of the representation theory of GLN of a finite field. Andrew Snowden and I prove it also is irreducible for F an infinite field. That was a fairly recent and remarkably difficult theorem, especially when F has an infinite field of characteristic T. That's not an easy theorem. But in any case, though, what's the about this thing? Borel and Serre do. So Borel and Serre is at the boundary of their bordification of the symmetric is homotopy equivalent to the building over. Okay, so it's not just that they construct a bordification of space as a manifold boundary. So for n equals homotopy, it's really the disjoint union of infinitely. So, but I don't really have time to, this is a beautiful tell for a long time if I wanted to. What does this mean? So, this was the Teach theorem was the key to their calculation of the cohomology dimension, because here we have a flow with boundary, and the boundary is itself highly connected, right? And that causes the dimension of the manifold to sort of cohomologically to drop. So that's how we calculated the cohomology dimension, but it also implies, so these are the cohomology of a manifold boundary. It's some version of Poincare, right? That version has to take into account the boundary. This homology relative boundary is what Poincare duality involves when you're looking at manifold. And when you try the language of groups, it turns out that here is the homology of the boundary. This implies something like the following. So the corollary is that the cohomology in degree n choose 2 minus of SLNZ with Q coefficients. I said this is supposed to be something like Poincare duality, so I'm going to say 4K of SLNZ. But here, I put the homology of the boundary. The boundary is that Steinberg representation. This is a coefficient system. You see these conjectures about the homology of SLNZ are really conjectures about the low-dimensional homology, but twisted by the Steinberg representation. And so all these theorems really a deep understanding of the action of SL and Z on the Steinberg representation, which is quite a subtle and complicated object. And I think I'll stop there. Thank you. Yes, Peter.
I emphasize that it's a manifold with corners, because you only need the topology of
Right.
differentials for.
Well, what's important, the reason I do care about the difference, because remember, if you're trying to do Hodge, doing Hodge theory, they had wanted to extend their differential forms over the boundary, and the boundary, you need a smooth structure to make that work, and so they don't have a so really you need the structure of corners to make sense of extending these differential forms over the boundary kind of objects at infinity.
I guess that leads
Yeah.
me to the next question.
Yeah.
I thought you can't do a Hodge theory on SL and Z because that's not a complex thing instead.
So Hodge theory, and there's two kinds of Hodge theory.
Okay.
So Hodge theory has there's a part of Hodge theory that manifold, and what you do is if you have a manifold with a Riemannian metric on it, okay, what you can do is you can you can compute cohomology using differential forms, right? But then there's a notion, so there's a Laplacian on different that comes from the metric, and a harmonic form is a form that's in the kernel of the Laplacian, and so the Hodge says that if you have a Riemannian manifold that's compact, boundary operators 0 on them, and so like literally, so that's the real Hodge, and the Hodge theorem in complex geometry actually is derived from the real Hodge theorem. What happens is if you have what complex Hodge theory is about Taylor manifolds, and these have special Taylor metrics. And so it's like a specialization but there's additional symmetry. Yes?
The initial two cases of mortification.
Right.
I imagine with the modular curve, you just would want to that one point at infinity.
You don't. So why don't you want to plug in that one point? So then you would change the topology, right? So it would become, instead of, if you just took the ordinary modular curve, that would go from a punctured sphere to a closed sphere, right? But this is supposed to be the interior of the boundary. So when you add a boundary, whole thing, right? What you really want is not to attach that single point at infinity, but to attach a circle at infinity. And that when you lift the pour it to a upper half plane.
Discrete set.
Turns out, okay, of for S. So okay, I'm going to draw something that's not quite it. So if you have a manifold that's the interior of a manifold of boundary, you can find the boundary inside it, right? You can push the boundary into a collar neighborhood. And so it's much easier to draw the boardification by not drawing the stuff at infinity, but in fact chopping off a neighborhood of it at infinity. Okay, it's an equivalent thing. And then I can just draw something in the upper plane. Let me tell you what you do is you take the upper half plane, get myself in a space to do this. So you take the, so here's the half plane, right? And what I do is I'm going to start off with a horoball. So the horoball here, I'm going to remove this. And so this I'm going to call this right here, that the imaginary part of Z is bigger than, say bigger than, okay? Anything bigger than 1. And so now, S2Z orbit of B, 2Z orbit of B. So here it is. So this right here is the SL2Z orbit of B. Well, any other image at a point other than infinity, right? Centered down here somewhere. And because I chose one, it's going to be disjoint from here. You can't, like, this right here, SL2Z can't, because it's going to take it to four balls. Disjoint balls. Etc. But then there's going to be more here. Packed very tight. Think about it. So what is the SL2Z orbit of the rational points on the boundary, right? Here is a disjoint union of balls. So centered at each point of Q, right? Each point on the boundary. And so now you remove those Hora-balls and you get Borel-Serre bordification, chopping off a neighborhood of infinity of the Borel-Serre bordification. What do I get? Well, except it's a surface of boundary. Each component of the boundary is a line. Right? These are not circles. So each of these is a real line, right? And so the boundary bordification, disjoint union, real line for each rational point plus infinity. Those are all slopes of lines inside Q squared, right? And that's how the Borel-Serre bordification works. Does that make sense?